Hi, welcome to your solutions video for your worksheet, parent functions, and transformations. I'm going to do this solution video for the multiple choice portions of this. We went over in detail these transformations in class, so I'm going to focus on the multiple choice. So let's scroll down here to our multiple choice and kind of show you the quick way to do these. So here I'm looking at when is this natural log negative, and I'm going to do it from a transformation standpoint. I'm going to think to myself what this function looks like, which would be my natural log graph with a shift to the right of 2 because of what's here. So you used to have a vertical asymptote here at 0. There's now going to be a vertical asymptote at 2. And then if you think about what your log graph looked like, it would then cross 1 away from its asymptote. There's no more stretching or shrinking. And it would be down and then come across like this. So this is here at 3 where there's an x-intercept. So just visually looking at it like this and looking at where the y values, because this is f of x less than 0, where are the y values negative? The y values are negative on this portion of the graph, which corresponds to x values between 2 and 3. So our answer to this is going to be C. All right, taking a look at 17. Now in 17 here we have our function e to the x, and we want to know which of the following lines is an asymptote to that. And remember, e to the x has a horizontal asymptote, so your horizontal asymptote would be y equal to 0. That's just knowing your parent graphs. Not much going on in that problem. Here in 18, here are my solutions to f of x equal to 0. And I want to know what are solutions to this. Well, basically, let's think about what do we mean when we say solutions. We have a function where your y is set equal to 0. So what they're basically giving you here at -1 and 2 are x-intercepts. So the function itself, we don't know what it's doing, blah, blah, blah here, but we're basically saying it crosses the x-axis at these 2 values. When I'm looking at the choice over here, now I'm solving f of x over 2. This is the same function with a transformation. You need to know what transformation this is. And when you have 1/2 of x, this is a horizontal stretch by 2. So it's going to pull the graph apart and make it twice as wide. So the question then becomes, what happens to these points here and here when I stretch them away? Well, if this was at -1, the new f of x over 2 gets stretched out to be twice as far away. And this is at 2, would go twice as far away, so it would end up at 4. So your new solutions to this are going to be at -2 and 4, which your solution would be E. And it's the idea of what would the new graph would still sort of have the same basic shape. It's just going to be kind of stretched out from what it was. Again, using the idea of transformations to solve problems. All right, this right here is just trying to test you on your knowledge of functions, that this is not multiplication. You are not distributing. This is bad. You do not think of functions as distributing because you're not multiplying. Only some functions, very few functions, have a property that allows that this and this are equal to each other. And you can test it. It's basically testing your properties. If I have, like here, you can just do a couple of examples. If I have e to the 2 plus 3, where you input a sum into the function, is that going to be equal to e squared plus e cubed? And clearly, if you know your exponent properties, we know that's not going to be true. Same thing is true here for e. If I check like that one, just to show you what's going on. If I do 2 plus 3 and I square it, so I add and then apply the function, is that going to be the same as 2 squared plus 3 squared? And you know that powers do not distribute over addition, so that one's out too. And so that's what we're doing. We're kind of testing if you understand whether this property, the sum of inputs, then apply the function, is that the same as applying the function and then summing the outputs? Are they exactly the same? Here for this one, let's test this one. If I have 1 over 2 plus 3, does that equal 1/2 plus 1/3? Hopefully you'll be like, yeah, no, not for fractions. You don't add fractions that way. And then we get here to our nice little linear function. So if I'd had to guess starting out this problem, I would say this is really true. It's very rare. So it's true for linear functions. Now I'm like, is it true for all linear functions? Let's see what happens. If I take f of 2 plus 3, I would have 2 plus 3 plus 1. Okay, so that's where I plug in, think of it like parentheses, and then add the 1. Or if I plug in the 2 plus the 1, and then I plug in the 3 plus the 1, and then I add those together, do I get the same answer? And that is, yeah, no, that doesn't work either, so that's out. And then we can test this last one. Again, if you plug in 2 plus 3, and then multiply by the 2, is that the same as plugging in the 2, multiplying by 2, plugging in the 3, and multiplying by 2? And that answer is yes. So kind of looking at it, the only time that this is true in these examples would be here for B. So again, we're just kind of playing on your order of operations, on making sure you understand that we're not multiplying here. We are actually applying functions, and that makes a difference. All right, here for number 20, I gave you a sign graph, and they just want you to find the equation. Well, basically, you have to know when you're looking at your equation the properties of transformations and how they affect sign graphs. I like to do the outputs first. It still has a midline of 0, so there's no vertical shift, but it has a maximum of 2. So that means there must be a vertical stretch by 2. So looking at that, we're going to be looking for a 2 on the outside. So B is gone and E is gone. So we take a look at that. Then I take a look at this idea. There's no horizontal shift, so that at least they're nice. They're not, combining a lot of things involved in it. It is a sign graph. All of these are signs, so that doesn't help me eliminate anything. But the period, when you take a look at this has a period of 2. The old period used to be 2 pi. So 2 pi times some horizontal stretch or shrink, in this case it's going to be a shrink, gives you your new period of 2. So your stretch or shrink is 2 over 2 pi, or 1 over pi, which means that in the actual equation, remember because of the flipping that we're always doing the reciprocal, that in the equation, the coefficient then B would have to be pi, the reciprocal. So we can eliminate this, we can eliminate this, so our answer for this problem is going to be C. We'll just fill in there. All right, let's take a look at 21. Which of the following does not have a period of pi? Well, when you think about just basic transformations, remember that it used to have a period of 2 pi, and so we would have to shrink it if we're just doing a regular tangent graph, or a regular sine graph. So this one, like you almost, if you're just looking at each of your choices, I'm going to be like, hey, that's the answer, because this is actually a horizontal stretch by 2, which would make the period of this graph be 4 pi. So that would not have a period. But now let's talk about why the other ones are okay. Sine itself has a period of 2 pi. But the minute you do the absolute value on the outside, remember that flips the bottom section up. So that graph is going to look like this now. And when it flips the bottom up, you'll notice that when it flips it up, now it does have a repeat every pi. This one, when you square it, same effect as absolute value. It does change the graph slightly. It's going to become slightly taller because you're squaring now. Or actually, if you square a fraction, it gets a little bit smaller. So let's back up for just a second. It's still going to have the same height that it had, which is 1, because 1 squared is 1. So this part's going to be in the same spot. But when you square a fraction, it actually becomes a little bit smaller. So it probably is going to be not as curvy, but then the negatives are going to do the same thing, and they're going to come up. These look very similar, but they're a little bit different because of the values that are right here. They'll be a little lower than the values over there, but still it will repeat every pi. Tangent has a period of pi, so that's just knowing your parent graph. Tangent squared, when you are flipping that one or squaring that one, yeah, you've got the positive side would be a little bit more stretched up. The negatives will flip and come up like this, but notice it's still going to have a period of pi because in between the asymptotes. So all of these have a period of pi. All right, looking at 22. Which of the graph has y equal to 1 as an asymptote? Natural log does not have, this is horizontal, so that has a vertical asymptote. Sine has no asymptotes. E to the negative x is a decay graph that decays to 0. This has y equal to 0 as a horizontal asymptote. Now we take a look at the two that are remaining, they're rational functions. You look at the degree. Degree of the top here is 2, degree of the bottom is 1, degree on the top is larger. That has a slant asymptote, does not have a horizontal asymptote. So this one, degree on the top 1, degree on the bottom 1, ratio of dominant terms, x over x equals 1. So y equal to 1 is your horizontal asymptote. So C is your answer. All right, fundamental period, very easy. Shrink of 1/3 times the old period gives us 2 pi over 3. So the answer for that one is A. Okay, we have a graph. We want to do the absolute value on the inputs. Remember, the absolute value on the inputs is going to delete the left side of the graph and then make it look like the right side of the graph. So our answer for that is going to be C. Then down to 25. Now this one, be careful because they're not asking you to transform parent graph x squared to get this. They're saying, what do you have to do to this to get that? First thing I notice is I definitely am going to need a vertical flip. So I'm going to need a vertical flip. Now the vertex after I flip it would be right there. And so from there, now let's see, do I need a stretch as well? If you look at, say, this point right here, from here to here, this nice point, we see that that is 1, 2, 3, 4. And then from this point right here over is 2. So I kind of check here as well. If I go from the vertex and I go over 1, 2, let me look at my 1, 2. Notice that you are going, it doesn't seem like you go up as much. So I think there's going to be a little bit of a shrink involved. So I'll keep that in mind. Okay. Or it might be a stretch. Maybe let's look at this. If I go over 1, 2, 3, and then up 1, 2, 3, 4. See how I now have over 3 up 4? So I'm going to say that there's going to be a horizontal, either horizontal or vertical. Let's say I can go over 1, over 2, up 1, 2. So maybe it's half as tall. So maybe we'll go with half as tall as what it used to be. And so I've got a vertical flip and half as tall. So looking at these choices down here, this has the vertical flip, but it doesn't have a shrink. This doesn't have the flip or the shrink. This has a shrink but no flip, so let's take that out. And then this doesn't have anything on the outside, so we have that. So I'm kind of process of elimination. Now, once I get that kind of taken care of, and you say, okay, now that I've done that, and if I'm shrinking it by 1/2, that's going to put your current location of your asymptote before I do any shifts right here because I shrunk it by 1/2. So then I have to say, well, how do I get from there to where the vertex is over here? And you're like, okay, so I'm currently at this location. I'm going to need to go down 1, 2, 3, 4 and over 1, 2, 3. Down 4 over 3. Down 4 and then to the right 3. Down 4, let me see it on the ones I have. Down 4 and to the right 3. So that's going to be E as my final answer for this one. So see, process of elimination. Think about what transformations happened, and you will get your solution. All right. And one last